Section 3.2, we're going to start working with polynomials a little bit bigger than just the graph of y equals x squared that we've dealt with. And to kind of get started, I want to acquaint you with an idea of multiplicity and also tell you how that affects the graph, or what you can see near the graph of a function and its x-intercepts. Let's start with this equation here. I can think of a graph of a parabola y equals x plus 3 times x minus 4. To find where this graph crosses the x-axis, you set the y-coordinate to 0. And I'm hoping that we can read this off. Where would the roots of this be? Where would the x-intercepts be for something like this? Where would -3 and +4? So those would be the roots. They correspond to where these things are equal to 0. Now, when you look at the graph of something simpler, y equals x squared, you want to know the same thing. And one way you can solve this is by factoring it. So you can say, all right, well, that's x times x equals 0. So where is this true? Where is that satisfied? Well, you've got a couple of choices, right? Either x could be 0 or x could be 0. Well, it's kind of the same thing, right? So what we say about this is that x equals 0 is a root with multiplicity 2, because that's how often it occurs as a root. So x equals 0 has multiplicity of 2. Okay, that's fine. What about if I looked at y equals x to the 4th? You're going to have something similar there, right? X to the 4th is going to have a root at 0, so it's going to have a vertex on the x-axis. But what's the multiplicity of that root going to be? Yeah, so x equals 0 has a multiplicity of m equal 4. So it's going to touch the x-axis at 0, and it's got this multiplicity of 4. So let's see what happens when we have a root of an even multiplicity. And for that, I'm going to do a little work on Desmos. Here's the graph of your parabola, y equals x squared. Here's a graph of y equals x to the 4th. Similar kind of behavior. Y equals x to the 6th. What would you expect from y equals x to the 6th? Similar kind of behavior again, right? So this time you have a root at 0 with multiplicity 6. So nothing really earth-shattering there, but you should see kind of a pattern here. In fact, let me kind of do it this way. Let's just change the value of n. To keep it even, we'll do 2, x to the 4th, x to the 6th, x to the 8th, x to the 10th. And you should see kind of a pattern. It has some kind of a U or parabolic shape, and it's symmetric. And in all cases, the parabola extends up and to the left and up and to the right. So they both point in the same direction. Let's take a look at some odd roots, though. In this case, y equals x cubed. This is a graph with that's going to touch the origin right here at 0, 0. What's the multiplicity of my 0 at the origin going to be? 3. So I get a graph that looks like that. And then x to the 5th looks like this, and x to the 7th, and so on. And a summary of these things, if you were to kind of look at them all together, would look like this. So for your even graphs, you're going to have this parabolic kind of shape, and it's going to be symmetric. For your odd graphs, greater than 1, or graphs with an odd exponent greater than 1, then you have a shape like this. And what I want to concentrate on is the behavior of the function at these points. So there's really 3 behaviors, and I've only discussed 2 of them. There's a behavior at the origin when you've got an even multiplicity, and there's behavior at the origin when you have an odd multiplicity greater than 1. If you actually had multiplicity of 1, then you get something like this. Your graph's going to pass straight through the axis. Whereas if you have something like this, an even multiplicity, what's happening to the graph when it touches the x-axis? Does anyone come up with a nice word for that? Let's go with bounce. So when you come close to the x-axis and you have an even root, your graph's going to bounce. And if you have an odd root greater than 1, then it's going to kind of do this little bit of a wiggle through. And if it's just n equals 1, then it's going to go straight through. And let me summarize those on a different sheet here for you. Like this. So, multiplicity of the root and behavior at the x-axis. So there's three possibilities. You could have a multiplicity of 1, in which case your graph, your function is going to pass straight through the x-axis. So that's one possibility. Straight through. You could have an odd multiplicity. M is odd and greater than 1, in which case you're going to have a wiggle through. And finally, you can have M is even and greater than 0. And what happened when you had an even multiplicity there at the root? Thank you. You had a bounce. So those are the three behaviors that you're going to see with respect to your roots. And knowing something about those behaviors and knowing something about what we call the end behavior is going to help you predict the shape of a function. So what's happening with the end behaviors then? Let's take a look at those. That's on the back of your handout. And I'm not finding mine at the moment. Where did mine go? There we go. The behavior of your polynomial is really going to be predicted by two things in this leading term. So here's a general polynomial. A sub n is the coefficient of your highest degree term, x to the n. And these two things right here, you really don't have to look much farther to figure out the behavior of a polynomial. So its eventual behavior, what happens in the long term, is going to be based on whether or not a sub n is positive or negative, and if the degree is even or odd. So if the degree is odd, then you're going to have something like this. Something like we had for our x to the third, or x to the fourth, or x to the fifth, x to the seventh. You're going to have something that goes down to the left or up to the right. So it'll be something that looks like that. Alternatively, if this number is negative, so here a sub n is greater than 0. If a sub n is less than 0, then the graph's going to get flipped, right? Because if you multiply this by a negative, then it's going to flip the graph. So you get something that, is going to look like this. Its eventual behavior is going to go down to the right and up to the left. If you have something that's even, a sub n is greater than 0, think of a parabola. Eventually, it's going to open up to the left and up to the right. It's going to have that kind of a behavior. Again, you're looking at the end-term behavior. And finally, if you have a negative in front of this, that negative is going to flip your graph. So this is when a sub n is less than 0. Your graph's going to open down. And let's do that here. And for convenience, let me give these some names. So let's call this A, B, C, and D. That way we can kind of quickly refer to these and see which behavior we expect. And we'll start by looking at problem number 68. So hang on to that and do a quick look at problem number 68. Problem 68 exhibits some of these n behaviors. We've got two graphs, y equals x 1.2 x to the 5th plus 3.75 x to the 4th minus 7x cubed minus 15x squared plus 8x. And we're going to graph this in comparison to y equals 1.2 x to the 5th. Now the point of this is that both of these should have the same end behaviors. Now before we started this video, I asked you to put those into your calculator. Let's put those in and look at it with an initial screen like this. So we'll look at it with a screen of -5 to 5 on the x-axis and -100 to 100 on the y-axis. Now I put y scale equal to 25 because if I didn't, then I'd have 200 tick marks crammed up and down the y-axis, and it really wouldn't be a very legible graph. So, okay, when you get that window set, here's our equation. Press the graph key. So here's the first one, and notice that it bounces up and down a lot and wiggles through our x-axis. So it looks nice. And then here comes the other one. And bam. Do these look like they're the same? No. Not at this level. But the thing is, the end behavior that this handout is talking about is what happens when the values of x start to get really, really big. What eventually happens. So by that, we mean for a larger scale. So let's do this. Hit the zoom or hit the Windows key. Now let's go, say, from -50 to 50 on the x-axis. And I can only imagine what it would be like on the y-axis, so I'm not going to try. I'm going to let my calculator do the work. Once you have the values of x set, it can set the values for y for you. Remember how to do that? It was zoom, fit. So zoom and then 0. And you don't have to even see it on the menu. Just type zoom and 0. And it'll adjust the y-axis for you so that it'll accommodate both your graphs. So here's one. You can see that along the x-axis is getting kind of thin. And here's the other one. Do they look very different? No. They're pretty much the same because the end behavior of this function is dominated by this term. In fact, in graphing this, basically I've ignored all these terms because when the value of x gets really, really big, this doesn't matter. If x was, let's say x was 10, then here you've got x to the 4th, 10 to the 4th, that's like 10,000. This is 100,000. So this is 10 times bigger. When these values of x get really, really big, this one dominates. So which of these 4 situations do I have here? Well, it has to be an odd function, and since my coefficient is greater than 0, it has to be a. And we see that. It's down to the left and up to the right. Now what happens in between? Well, that can wiggle around a lot, and we saw that with our initial window. But here, we're seeing the long-term behavior of this, the end behavior, and they're much different. You can see that again looking at problem number 46. Let's see, where do I got 40? So 46, and we're not going to graph it. I'm just going to put it up here for you. P of x is negative 1/8 x cubed plus 1/4 x squared plus 12x. And then q of x is negative 1/8 x cubed. So those two should look pretty similar at kind of a zoomed out level. And if you look at the back side of your handout, you'll see exactly that. If you look at it with a viewing window of -4 to 4, you're going to see some differences. But when you zoom out, and I've got something close to like negative 50 to 50-ish, is there really much of a difference between those two? They look pretty similar. You're getting the same end behavior. So you can really make good predictions as to what a graph's going to look like eventually. And that's one of the goals here in this section, is to make those predictions. Now, we're going to start putting a couple of these things together. By the way, which one of our graphs would relate to 46? Which one of these? B. You've got a negative leading coefficient and an odd degree. So, we've got our odd degree and negative leading coefficient. Yay. Let's start applying these to some actual problems. And we'll start with problem number 10. Problem 10 looks like this. Q of x is negative x squared times x squared minus 4. And if you were to distribute this, I'd get negative x to the 4th plus 4x squared. And the only reason I want to distribute that is to just give us a good look at what this polynomial is, so we can decide what its end behavior is. So take a moment and decide which one of these graphs, A, B, C, or D, is going to show its end behavior. D. So you've got an even degree, so you're here, C or D, but because the leading coefficient is negative, it's going to have to eventually open down on both ends. So, okay, let's keep that in mind. Now I'm going to work with this one a little bit. That's negative x squared, but this term will factor a little bit. How does x squared minus 4 factor? All right, good. X minus 2 and x plus 2. And with that, I can help myself out a little bit. Let's look at the different binomials here. We've got a binomial at, say, x plus 2. We've got a binomial at x minus 2. And another one at x. I know a few of you might want me to write down the x squared, but I'll take care of the squared in a different way. Now, what we're looking for quite often when we're dealing with polynomials are the roots. Where do these things cross the x-axis? So basically, I'd want to know where that's equal to 0. Well, that's going to equal 0 when, let's see, well, one of the possibilities is that x could equal what? Minus 2. Or another one is that x equals 2. And the last one is that x equals 0. Well done, in unison. You're making me look good. Thank you so much. What about the multiplicity of these roots? Multiplicity. Well, let's put some numbers up here. Even though they're not really written, let me put up a couple numbers here. The exponent here is understood to be a 1. The exponent here is understood to be a 1. So the multiplicity of this is 1. The multiplicity of this one is a 1. what's the multiplicity of my root at the origin? At 0. 2. And that tells me something about the behavior. So the behavior of the root at this is going to be that the graph at this point is going to pass straight through. Straight through. And I'm just going to abbreviate it ST. But what happens at the origin? Bounce. Wow. So between the end behavior and the behavior here, we have a really good idea. We haven't touched our graph at all, have we? But we have a really good idea of what this graph looks like. It has to open down on both ends. It's going to cross through the x-axis at 2 and -2. It's going to have a little bounce at the origin, at 0. So, with all that in mind, let's see if we can't narrow down which graph it would be. So, I'm giving you 4 choices. We can eliminate these 2 choices. Does anyone know why? These are odd functions. These are odd polynomials. So it has to be one of these 2. And both of them cross through the x-axis at the right spots, 2 and -2, and a bounce at 0. But which one of them has the proper end behavior? The first one. So, yeah. Remember, our end behavior is going to be facing down. So without ever touching your graphing calculator, we know exactly what this thing looks like, or at least a lot about what this looks like. So this one turned out to be 1. Okay, we did a lot of work to get here and to do this one. So before I move on to another one, do you want to follow up with anything? We're okay on that one. I think the next couple should work a little bit faster. Let's try problem number 14. U of x equals -x cubed plus 2x squared. Well, it's nice that we have it written like this, but I'm going to take the effort to factor out the -x squared. And that leaves me with something like this. We're going to do the same thing that we did with the last one. You can probably expect to use a chart like this on your exam. IOR. First things first, what's the end behavior of this one going to look like? Is this going to be A, B, C, or D? Yeah, this one's going to be B. You've got an odd root. There's going to be an odd degree and a negative coefficient there. So this one's going to have behavior of of B. Let's look at the different terms here. We've got a term at x and a term at x minus 2. That gives me a root here at 0 and a root at x equal 2. What are the multiplicities of these roots? Yeah, multiplicity here is 1. Excuse me, multiplicity here is 2. Multiplicity here is 1. It's not written, but it's understood that there's a 1 here. The behavior, bounce, and straight through. Let's see if we can't figure out what the graph of this is going to look like. And based on our work just a minute ago, we're going to have a couple of different choices. has to be one of these two because these are the only odd graphs that we have. So which one do you think? It's going to be 3 or 4? 4. Yeah, it's going to be 4 because it has the proper n-term behavior. Nice. So 4. Oops. 4. There we go. Okay. Let's take a look at problem number 26. Problem 26 is on the opposite side of your handout. And fortunately for us, this is already factored. And I've given you the same kind of chart that we've been using. So let's look at our binomials. There's 1 at x plus 1. There's 1 at x minus 1. And 1 at x minus 2. These binomials correspond to different roots. So what's the root that this one corresponds to? Thank you. X equals -1. X equals, what else? 1. And x equals 2. Now what are the multiplicities involved for these roots? All right. So at -1, you have a multiplicity of 2. What about at positive 1? 3 and 1. Now, if I multiply this all out, 2 times 3 times 1, I'd have a 6th degree polynomial. So 6th degree. Let's look at the behavior of the function near these roots. So the behavior near these roots, well, that's going to be a bounce, and then a wiggle. What's the last one? Straight through. All right. Let's see if we can't put this onto a graph then. Well, we need to know and understand the n-term behavior. Which one are we looking at for the n-term behavior? A, B, C, or D? D. It's eventually going to open facing down. So, n behavior is D. And on the back side of your handout, you'll see that n behavior. So there's your n behavior. I've already kind of drawn them in for you. But let's see if we can't fill in a little bit of the rest of this. Where do we have roots? We had roots at -1, 1, and 3. Or excuse me, -1, 1, and 2. So at -1, we had a bounce. At 1, we had a wiggle. And 2, we had a straight through. Here, and here. So let's see if we can't figure out what's happening with this graph without even looking at our graphing calculators, although you're free to look at them. But it should just really confirm what you're seeing. Now, as the graph of this function approaches -1, what's going to happen to it when it touches the x-axis? What's it going to do? It's going to bounce. So, since you're starting from down here and coming up here, it has to bounce. It's going to ricochet and come out. And then, let's see. Yeah, that's going to come over through here. And what happens when it goes through here? It wiggles through. So it's going to start out below the x-axis and wiggle through and then come up here and now it has to go straight through. So something like that. Now you can sharpen that up a lot by looking at your graphing calculator, but this has to be roughly what the shape looks like, and we didn't look at a graphing calculator at all. So, all right, that's good enough for today. For homework, just try problems 5 through 25 to get you a good start, and we'll do some more on this next time.